bias. Okay, and same way, you see, we assume the current flowing through RC is IC plus IB, and this current is splitting it as IC here and IB here. Okay, so this current which is flowing through RC is IB plus IC, and the current flowing through RB is IB, and the current entering the collector terminal of a transistor is IC. So you apply KVL in this path, you apply KVL in the base side, this path. If you apply KVL in this path, naturally you have two voltage source, VCC and VB, and VCC and VB are opposing. So VCC minus VB equal to two resistance I have. Current flowing through RC is IC plus IB. And here only it is splitting. Okay, current flowing through RC is IB plus IC, and current flowing through RB is only IB. So from this, you group the IB terms and you get the expression for IB. And we want differentiation of IB with respect to IC because I need to substitute this in my stability factor equation. So when you differentiate IB with respect to IC, the first term and second term will become constant, so they will become 0. Only the third term will give minus RC by RC plus RB. So substitute that in the stability factor equation. So S is equal to 1 plus beta by 1 minus beta into this term. This has a minus, so minus of minus will become plus. So 1 plus beta by 1 plus beta into RC by RC plus RB. This is the stability factor for your collector to base bias. As here also you see this 1 plus beta by a big number. So stability factor has been reduced from 1 plus beta to a value less than that. How much it is reducing will depend only on the parameters you apply, and you find out the stability factor for this expression. Okay. So you can see that the stability factor is very, very small compared to the fixed bias. With respect to fixed bias, you can definitely get very good stability, and you can even make the stability factor small by changing the value of RB or RC. You see, S value should be less. If S value has to be less, denominator has to be more. If denominator has to be more, then RB should be made high, RC should be made high, and RB should be made small. See here, RB should be made small, or RC should be made large. If you may do that, denominator will be large, so S value will be very, very small. So if RC is very, very small, if you put RC equal to 0, it will be approximately equal to 1 plus beta, which will give you a very good, very poor stability. It is just like a fixed bias. When you put RC is very, very small, when you put RC equal to 0 in this equation, you can see the denominator is completely vanishing to 1. So S becomes 1 plus beta, which is the stability factor of your fixed bias circuit. Already we have seen that this 1 plus beta value is very, very large. So fixed bias circuit will have a poor stability. That's why we are saying that RC value should be very, very large and RB value should be very, very small for having a very, very good stability factor. So this is this collector to base bias arrangements is not satisfactory for amplifier circuits because see, when you reduce the value of RB, base terminal might have a larger value of IB. So the base terminal might become in the danger of accepting very high current. So that is one drawback in the circuit. So our condition is for better stability. We are told RC should be large and RP should be small, right? If RP is small, then the base current will start increasing, so which might damage your circuit. So that is the only drawback in the thing. Otherwise, this biasing circuit has no drawbacks. It is going to perform in a very, very effective way compared to the previous circuits, whatever we have studied. Only drawback is by reducing RB, we might have a possible danger of having a larger base current which is going through your transistor. That might hamper the Q point of your transistor.